baffling planet has piqued the interest of researchers and space fans alike. The James Webb Telescope has just reported the most clear picture of Proxima ever seen in history. What secrets does this far-off world hold? Might it ever support life? Let's dive into what the James Webb Telescope has uncovered. Thinking back billions of years into the universe's set of experiences, we can glimpse how systems appeared. With the James Webb Space Telescope, JWST, we can take that guideline to the following level and investigate the uttermost compasses of space. The infrared pictures caught by the JWST are unlike anything organic eyes have ever seen before. The telescope's capabilities truly rely on how it's used, similar to a Snapchat channel on your telephone. The James Webb Space Telescope empowers space experts to study the early universe and better grasp the birth of systems, stars, and planets. Analysts can break down the shades in those pictures by utilizing the telescope camera and channels to assemble a particular scope of light tones. The JWST will likewise explore the atmospheres of planets outside our nearby planetary group and quest for signs of extraterrestrial life. Its capacity to look further back in time and space than at any other time has prompted critical discoveries on the development of the universe. For instance, cosmologists utilized the telescope to find more mass than previously accepted to exist in the universe, stowed away in several massive systems. The James Webb Telescope has just declared the most clear picture of Proxima ever found in history. In 2013, stargazers identified traces of a small gravitational pull applied by a planet on its star. Following quite a while of looking through the planet which circles Proxima Centauri, was subsequently named Proxima B. The disclosure of this planet is fascinating since it circles the nearest star framework to us after the Sun. Noticing the Alpha Centauri framework, which is around 4 light-years from us, gives a brief look into the past since we are seeing it as it was 4 years prior. Proxima B unquestionably takes the cake with regards to invigorating galactic disclosures. This planet is found a simple 25 light-years from Earth, making it one of the nearest exoplanets at any point found. Yet, don't let the distance fool you. Proxima B is a whole different world from our own. The planet is around 30% more massive than Earth, and that implies it's bigger as well. Yet, don't let that fool you. Proxima B's year endures only 11.2 Earth days, which is super short. That's because the planet circles its star, Proxima Centauri, at a distance of just 7.3 million kilometers. That's not exactly 5% of the distance among Earth and the Sun. You may be feeling that a planet that is so near its star should be extremely hot. However, Proxima Centauri is a little red small star that doesn't transmit almost as much energy as our Sun. So what might it be want to remain on the surface of Proxima B and look up at Proxima Centauri? The star would look like a dull red sphere approximately multiple times as large as our Sun. And assuming the planet is in its star's tenable zone, which it appears to be, it could have the right circumstances to support fluid water. Yet, before you begin gathering your sacks for an interplanetary experience, you ought to be aware that Proxima B is nowhere near a second Earth. For one, the planet is reasonably clean locked with its star, which implies one side faces the star while the other is continuously in murkiness. That's certainly not an agreeable climate for any potential living things. And that's what any water comes excessively near the star would be reduced away by its strong radiation. On the other hand, if a planet is excessively far from its star, it will not get enough intensity and its water will freeze. Proxima Centauri probably won't be as well disposed to life as we naturally suspected. Regardless of having just a negligible part of the Sun's mass, its little size causes its atomic combination center to be a lot nearer to its surface, coming about in tumultuous and violent surface movement. This activity prompts incredibly strong attractive fields that produce high-energy radiation and molecule blasts, presenting a huge challenge for planets like Proxima B that circle inside the star's tenable zone. While researchers had some information about the attractive field conditions around neighboring stars, they were in the dim about the exact circumstances around Proxima Centauri. As of recently, due to a recent survey utilizing high-resolution attractive field maps, we better comprehend the star's sunlight-based breeze and the critical circumstances on Proxima B. The review uncovered that the planet gets multiple times more sunlight-based breeze radiation than Earth, putting any expected life in danger from strong flares. As a matter of fact, A Proxima Centauri flare in April 2021 was multiple times more strong than any flare at any point saw from the Sun. It's difficult to envision life making do such extreme radiation without specific haven. While the possibility of a habitable planet circling Proxima Centauri is enthralling, the reality appears to be a long way from cordial. As people, we have forever been intrigued with the chance of experiencing extraterrestrial life. And in late 2020, that interest arrived at new levels when an unconventional signal was found originating from the Alpha Centauri framework. Strangely, this sign peruses at an unexpected recurrence of 9,827 MHz, which isn't commonly related to signals from Earth-based satellites and shuttles. While some specialists theorize that a piece of made hardware might have caused the sign, others keep on dreaming that it very well might be verification of canny life venturing out to Proxima Centauri, the nearest planet outside our planetary group. Experiencing outsider life may not be as fantastical as once suspected. The advancement drives have been investigating the chance of cutting down movement time from many years to just many years. Ongoing exploration features how current innovation could possibly overcome the challenge of speeding up an object as its mass increments, especially as it moves toward the speed of light. In spite of this, Alpha Centauri, being the nearest star framework to Earth, would still expect something like 6,000 years of travel time with current innovation, making it an overwhelming excursion. Starshot, a project aimed at arriving at Alpha Centauri, is taking into account utilizing lasers to move a rocket toward its objective. However, the principal challenge lies in the Earth's atmosphere, which influences approaching light and laser light, making it challenging to apply the necessary power to push a rocket ahead. That's what paper's most memorable creator suggests. Versatile optics could be utilized backward to overcome this challenge. Small lasers on satellites would survey air impacts progressively, permitting significantly more strong lasers on the ground to keep a tight spotlight on the space test. The expected lasers need a whopping 100 gigawatts of ability to send the vessel at some random time, which is comparable to the whole power utilization of the US. However, the lasers only have to run at most extreme limit for 10 minutes to scatter the power across a kilometer-square region. They intend to utilize 100 million lasers. The Starshot, not entirely set in stone to push the limits of room investigation. The object rushing through space will be moving at a shocking 20% of the speed of light when the lasers are switched off. This shuttle would be a little north of 10 meters in breadth and could arrive at Alpha Centauri in only 22 years. However, the gravitational draw of the Sun and interstellar flotsam and jetsam may significantly dial it back. Regardless of whether the shuttle arrives at Alpha Centauri, its transmissions will take another 4 years to arrive at Earth. Bope and Siegler know that holding the test back from softening is one of the greatest difficulties. To forestall this, the mirror on the rocket should be practically great, reflecting 99.99% of the light that strikes it. Moreover, it necessitates to twofold the energy move while diminishing intensity surprisingly fast. Once sent off, the test would cross the Alpha Centauri framework, probably never getting extremely close to a planet. The fascinating piece of this idea is that once the send-off framework is set up, additional tests might be sent for a sensible value. The possibilities of getting a temporary look at any Earth-like planets are essentially expanded if an armada of tests floods adjacent star frameworks. Imagine the potential outcomes. In the wake of showing up at Proxima Centauri, humanity would have a whole star framework to investigate. How many extra planets like our own might there be? Exoplanets are planets that circle stars outside our nearby planetary group, and the disclosure of these far-off universes has revolutionized how we might interpret the universe. Thousands of exoplanets have been recognized since the early 1990s, revealing an astounding variety in planetary frameworks and their qualities. This journey of discovery started in 1992 when researchers made the first official discoveries of planets surrounding a specific class of neutron star known as a pulsar. It was an unexpected and pivotal discovery, since pulsars are remainders of cosmic explosion blasts characterized by their extreme radiation and quick pivot, making them seemingly threatening conditions for planet arrangement. The pulsar planets were a curious find, but the mission for planets circling stars like our Sun went on. In 1995, this mission proved to be fruitful with the discovery of 51 Pegasi b, the first exoplanet found circling a Sun-like star. This planet, situated around 50 light-years away in the group of stars Pegasus, was a hot Jupiter, a gas giant circling very close to its star. The discovery of 51 Pegasi B denoted a significant achievement, demonstrating that other nearby planet groups could indeed exist and could be altogether different from our own. From that point forward, the quest for exoplanets has expanded emphatically, helped by headways in innovation and observational techniques. Ground-based telescopes, for example, those at the Keck Observatory in Hawaii, have played a fundamental role. However, it was the send-off of space-based observatories that truly sped up the speed of discovery. The Kepler Space Telescope, sent off by NASA in 2009, was particularly extraordinary. Kepler observed more than 150,000 stars in a small fix of the sky, searching for small plunges in splendor brought about by planets traveling or passing before there have stars. Kepler's main goal was remarkably fruitful, distinguishing more than 2,600 affirmed exoplanets and great many extra up-and-comers. These revelations incorporated a wide assortment of planets, from small rough worlds comparable in size to Earth to colossal gas giants a lot larger than Jupiter. Kepler's information uncovered that planets are normal in the Milky Way world, with an expected 1 in 5 sun-like stars hosting an Earth-sized planet in its tenable zone, the region around a star where conditions may be ideal for fluid water to exist. Among the various exoplanets found, several have accumulated specific interest due to their capability to help life. These are essentially Earth-sized or slightly bigger planets situated inside their star's tenable zone. One striking model is Kepler 186f, the first Earth-sized planet found in the livable zone of its star. Situated around 500 light-years away, Kepler 186f circles a red small star and gets around 13% of the energy from its star that Earth gets from the Sun. Its revelation was a significant achievement in the look for livable universes beyond our planetary system. Different missions have constructed on Kepler's heritage, including the Transiting Exoplanet Survey Satellite, TESS, sent off in 2018. TESS is studying almost the whole sky to find traveling exoplanets around the more brilliant stars, making it simpler for follow-up observations. Meanwhile, the James Webb Space Telescope, JWST, set to begin operations before long, will give exceptional bits of knowledge into the environments of exoplanets, potentially identifying indications of livability or even life. The disclosure of exoplanets has significant ramifications for our comprehension of the universe. It recommends that planetary frameworks are normal and that the cycles that drove to the development of Earth and the other planets in our planetary group are not extraordinary. This raises the tempting probability that life in some structure would be able to exist somewhere else in the universe. As innovation propels and our observational capacities work on, the investigation of exoplanets will keep on being one of the most intriguing and dynamic fields in cosmology, bringing us closer to addressing the deep-rooted question of whether we are distant from everyone else in the universe.